Hello, my name is Noah Hantho. I'll be doing a presentation on my massively open online class, Gravity, specifically on weeks 3 and 4, Cosmic Inflation and Dark Components. Okay, so in the beginning of time, the universe shifts from an opaque kind of wall to a transparent universe as hydrogen recombines, and everything becomes transparent and becomes more of what the universe we know today. Um, if we look 15 billion light years away towards the beginning of the universe, we would see this same opaque wall because this is the beginning of the universe. This black body, which is heated at 3000 Kelvin, um, emits radiation characteristic of its temperature. We see spectrum of this radiation. Planck explains this spectrum of radiation by concluding emission was not continuous, but that light was actually emitted in grains, which we call photons. The energy of these grains was proportional to frequency. Engineers of the Bell Labs built a large antenna to detect radio and microwaves. They detected a noise that they concluded after many tests must be a signal of the cosmological black body. The radiation was identical from all directions, which means it was homogeneous and isotropic. Causality plays an important role when we discuss cosmology. For instance, if Millard were to spill his coffee at the beginning of the day because he was so deeply engrossed in reading Einstein's theory of relativity, Einstein's theory of relativity caused Millard to spill his coffee. But Millard's spilling his coffee had nothing to do with Einstein writing his paper. Event 1 affects event 2, but not the other way around. Horizon also helps us to deduce the fact that the Earth must be round because you see boats disappearing over the horizon. This means there must be surface beyond what we can see. We use this example to help us explain how we cannot see beyond 14 billion light years away. There is stuff out there, but because information cannot travel faster than the speed of light, we can only see to a certain radius. Inflation is the expansion of the universe, which is very rapid and faster than the speed of light. 2 points that could send information may not be able to send information after inflation because information would have to travel faster than the speed of light. As the universe expands, the 2 points would get so far away from each other that they would no longer be in contact. They'd be outside of the radius of being able to send information to each other. Photons of the cosmic microwave background are causally connected because they come from the same region of the universe that expanded outward after the Big Bang. So as the universe expanded, these points expanded with it. So they're causally connected by event 1, the Big Bang, but not by event 5, where we are now. In everyday language, the vacuum is what remains from what we take away in everything in space. Is what remains when we take away everything in space. In the quantum world, things are a bit different. For example, if we had a particle and an antiparticle, say an electron and a positron, created out of a vacuum, the electron has a mass, so it has energy mc squared. The anti-electron also has a mass, so it has energy mc squared. When we add them, we get energy 2mc squared, which appears to be a contradiction to the conservation of energy. Quantum physics tells us that this is allowed as long as it lasts a very small amount of time. It is allowed as long as after some microscopic time, the electron and anti-electron annihilate again into the vacuum. However, many fluctuations, just like this one, are occurring at the same time throughout the vacuum. Just like that. So they contribute to the energy. We call this the energy of the vacuum. This energy is the engine of inflation. Dark matter was first identified by Fritz Zwicky in 1993. Zwicky was measuring individual velocities of galaxies as they move outward because of expansion. In order to do this, Zwicky wanted to measure the mass of a cluster of galaxies. To his surprise, the mass was 400 times more than what he measured from luminosity. This means that there was much more mass than what is luminous. This was the birth of what we know now to be dark matter. Essentially, we now think that there's a spherical halo of dark matter surrounding the luminous matter of a galaxy. Another way to identify the presence of dark matter is to observe the curvature of light rays around a mass. Light rays from another galaxy take a curved path to our eyes on Earth due to the presence of dark matter. Because of the curvature of the light rays, the galaxy we witness is a distorted image of the galaxy in its true form. If two galaxies were to collide in space, the luminous matter would get disturbed. They get all distorted and go crazy when they hit each other because they strongly interact with each other. However, the dark matter from both galaxies would simply pass through undisturbed. They interact very weakly with other particles. Dark matter is the main form of the universe. We've now discovered that it takes up most of the mass and energy of our universe. Detecting these dark matter particles, though, is tricky. Perhaps a dark matter particle comes down from the cosmos. And it hits a proton that is in a detector on Earth. Sorry, I lost my place. After the interaction, the proton is kicked out of the detector and the dark matter particle leaves. We therefore detect that it was a dark matter particle kicking this proton because it was an unknown force that disturbed this proton. So we can conclude it was dark matter. We can conclude this because this detection facility would have occurred way underground, at least a mile. And so the only sort of particle that could get down there would be a dark matter particle because it weakly interacts with the matter around it. So it could only be a dark matter particle. If we had done this on the surface, it could be some other sort of light ray or anything from out in space. But since we do it a mile underground, we can infer that this was actually a dark matter particle. Inflation tells us that because of rapid expansion, our universe is indeed flat. We've tried to figure out the geometry and size of our universe by using the luminosity and distance of stars to map it out. However, this becomes very difficult because it is hard to calculate if a star is luminous simply because it is close, or because it is young, or if it is actually more luminous. We have now, however, found a constant in supernova explosions which occur at the death of a star. These explosions are identical whether the star is old, far away, or new, close. This constant value of luminosity makes it easier to map where the stars are and how our universe is expanding. Teams measuring these explosions realized that these stars were moving farther away in between tests. This indicated that the expansion of the universe was accelerating. Scientists were delighted because this surprise was a missing link to the puzzle of the flatness of the universe. Why was finding out that the expansion of the universe is accelerating so surprising? Well, we have seen the universe is expanding because of gravitational force. This is one of the consequences of Einstein's equations. We've also seen that matter tends to attract each other in space. It's two matter attracting each other. And that the presence of matter decelerates expansion. The presence of light also tends to slow down expansion. Electromagnetic radiation and matter were supposed to be the two biggest components of the universe. Finding acceleration and expansion meant we had to find a new component. We are calling this new component dark energy. It will account for 70% of the energy of the universe. The other 30% comes from luminous and dark matter. The energy of the quantum vacuum, or vacuum energy, is presumably what provides for this dark energy. We think this because the vacuum energy accelerates just like dark energy. To explain a vacuum better, we will use this diagram which shows the vacuum as the fundamental state of matter, here with one particle. When we introduce another particle, we get another level of energy, 2mc squared. Then, as we introduce another, 3mc squared, and a fourth, 4mc squared. This concept is hard to understand because we are used to there only being one fundamental state, with one particle and one level of energy. To explain how the vacuum of energy accelerates the expansion of the universe, we use an illustration of two elevators. One elevator falling over the sun, and another falling over a vacuum. The two elevators simulate the expansion of the universe. The one over the sun is being accelerated upwards by radiation, so this light slows down the expansion. The one over the vacuum is pulled down by the particles that it is attracting, so it accelerates expansion. That is a summary of what I've learned from weeks 3 and 4 of the MOOC Gravity, Cosmic Inflation, and Dark Components. Thank you for your time.